recently at the IFA, now down on campus.
Wonderful.
Why, Institute of Physics? I see you have a fan club already. Okay, go ahead.
Our title is Space Weathering of Olivine in S-complex asteroids. And I'm Jasmine.
And I'm Evelyn.
So, what is space weathering, you may ask? Well, it's very similar to the weathering process on Earth, where rocks are eroded by wind, as an example, and it's used to create small particulates. However, this occurs outside of the Earth's atmosphere, where celestial bodies are being altered by the harsh conditions in space. For example, solar winds, solar radiation, and micrometeorite impacts, which will be our primary focus in this project.
So we were looking at olivine, which is a green-hued, as you can see here, iron and magnesium-rich silicate. It is found on Earth, but we were looking at it as primarily prevalent as being in S-complex asteroids and subtypes primarily 1 through 3. And then here you can see that it is mixed with basalt, and that's going to be closer into the subtypes later. So the latter subtypes more towards the 3 to 4 area.
So to classify these asteroids into the different subtypes that she mentioned, we use a process called asteroid spectroscopy. Here on this slide is an example of different spectra for S-complex asteroids. As you can see here, these are absorption bands, these dips or curves. And we use similar graphs for our mineral olivine by collecting the spectra. And olivine dominates subtype 1 of the different subtypes in S-complex asteroids.
So she's been talking about subtype 1, but what is that? So here we have different subtypes. As you can see, this here, this area, sorry my hand's not very still, but this area is subtype 1. On the bottom here we have band 2 and the band 1 area ratio, and then on the side here we have the band 1 central wavelength. So what this means is that there are different bands, and she said the dips, so the curves and the dips. And what we're looking at is band 2, so the latter dip, compared to band 1, the former dip, and the area ratio between the two, and then also the band center. So as you saw in the last presentation, which is great, they went before us because they showed that there is that band center there, and that's what we were also looking at as being this side area. So for the band 2 to 1 ratio, we have, for our mineral specifically, being the S1 subtype, it shows that it is being closer to 0, meaning that the band 2 is a lot smaller. It's a much smaller dip and depression than the band 1 depression is, and that's shown by it being closest to 0 rather than more equalized near 1 and then even greater.
So to simulate the effects of micrometeorite impacts, a high-powered laser was used to irradiate the samples of olivine. So here, the blue spectrum represents a fresh sample of olivine, whereas the lilac spectrum represents the most weathered sample. And as you can see here, these are the absorption bands, and that was also shown in the S-complex asteroid graphs. And they have a bigger dip here than they do in the most weathered sample.
And more on that, we were also looking, as they said earlier, oh dear, that's wrong. Okay. Technology, guys. So we were looking at between the shoulders. So in this case, this is a shoulder, and then over here is going to be shoulder, and then there's this tiny little dip here, so this is a shoulder, and that's a shoulder. And we were looking at the area, so when we say the band area, it's this area that's filled inside between the two shoulders, as seen later by the continuum. So
here we scale the data, or normalize the spectrum. And with that, we divide each spectrum by a certain value corresponding to a certain wavelength. So for here, it's 0.5. And this is used to isolate the slopes. As you can see, the slopes actually get steeper as a function of time, or get redder as it reaches infrared.
So based on these graphs that we showed just now, we were wondering, okay, so we see that there are changes. There are lots of changes. But what does this mean for the subtype? Does this mean that it will completely change what subtype our mineral is in? And that's what we were investigating.
So as she said, the absorption band represents the region where the mineral absorbs the most light. Here is band 1 and band 2 of the freshest sample, and here is band 1 and band 2 of the most weathered sample. So we isolated the absorption band, and we made a continuum fit from one shoulder to the other. And with this, we are able to calculate the area of the absorption band by subtracting the spectrum line from the continuum fit. And we're able to make a ratio of both.
And that is what we have here. So we have band 2, which would have been that shallower band over to this side. And the band 1 would have been the more depressed and deeper band over to your other side. So here we have, as you can see, there's kind of a positive trend. And this is as weathering increases, so does the ratio. But if you look at the scale here, it might look like it's a larger increase, but if you look at the scale over here, you can see that they're very, very minute increases. And this just shows that although there is slightly a positive correlation between the weathering in minutes and then also the equalization or the equalization of the band ratios, it also shows that the bands are moving together, because otherwise, so when I say together, you have your two bands, and as it gets more weathered, the bands start to move up together more proportionally, rather than if one were to move and the other were to stay the same that it was, we would see much more drastic differences.
So after collecting the ratios from the previous slide and the band 1 center wavelengths, which is used by the process of continuum removal, we're able to plot the data, and we found that the values remain in this subtype, and although there are slight variations, it's not drastic enough to actually move into a different subtype.
So in conclusion, what we found was that weathering decreases the band area as well as creates a slight increase in the band area ratios.
There's a slight shift in the band centers to higher wavelengths, and there's a decrease in reflectivity.
So overall, we observed many different changes, but we found that none of these changes were drastic enough to reclassify the mineral itself into a new subtype. So, here are our people. We have our wonderful directors. Where are you guys? I can't see anything. Where are you all? Okay, so
did
there.
that on purpose.
Okay, so we have Mr. Matthews, Mr. Nasser, Mr. Armstrong, sorry, where's Michaela, and then our High Star supporters. So that includes our friends at High Star, but all the parents as well who sent your children here to get learned after a week. And then we have our mentor, which is absolutely, she's the most wonderful mentor ever. She's great. And so thank you. Any questions?
It looks like a Roy in the back.
So you talked about the weathering as units of time or minutes. Is that sort of kind of cosmic time scale with 1 hour of laser firing corresponding?
Oh God, I'm so happy I asked this question. what it equals out to being is around 800 million years, give or take, for the distance from Earth to the moon of micrometeorite impacts on a certain sample.
800 million years for 60 minutes?
Yeah, so 60 minutes is equivalent to approximately 800 million years.
Just following right up on that, is that corresponding more to the irradiation or to the micrometeorites or to the space weather? Because these three different effects may have different
Okay,
causes.
that's a good question. Oh no, I don't want to say something.
That's right.
Okay.
So the mentor happened to be sitting right next to you.
Okay, so I'm gonna go out on a limb and please correct me if I'm incorrect, but I think it's more directly correlated with the micrometeorite impacts because it creates heat, and we were and it kind of melts the surface particulates. So that's what we were looking at is mainly not the solar wind or the solar irradiation, but the micrometeorite impacts themselves. Yeah.
Okay. Great. Yes.
So I was very interested in the plots that you showed, which showed what was happening in the time sequence, both in terms of the interpretation of how the slope was changing and the relative depth of the feature. What I was most curious about, however, was in the laser impact simulation where you see that the reflectance is changing much more at the shorter wavelengths than at the longer wavelengths. This is basically the curves are dropping and becoming much steeper. Is that an actual representation? Is that a good representation of what you see if you look at, different samples, like fresh samples versus old samples in, layers that are exposed to different degrees of weathering? Do you know?
Okay.
And I have no idea what the answer would be, but I'm just curious.
Okay. I'm not sure if we do either. We're gonna think about
I'm
this.
gonna try and answer. So I asked my mentor how many spectra she or a normal scientist or an astronomer would usually work with, and she answered with millions. And although this is a compressed version of that, we also did standard deviation, and but the values that we found were very minute.
I guess, okay. Not sure. Yeah.
If you'd like to add something more.
Yeah. I'm gonna go with there are differences, and that definitely at different depths there's gonna be different differences. For the laser impacts, I think that we could mix the sample itself, so the right was just the sample mic, so that everything got kind of.
I'm not sure if she's asking about asteroids or powders. Are you saying, do you actually see this on asteroid samples?
So my question has to do with using the laser to simulate, the time scale of this, versus what we think is happening on the actual surface. And that is, if I looked at surfaces, I'm trying to compress what's going on over large periods of time.
Yeah.
What I don't know, I know that I'll see these effects if I use a laser to
Are
simulate
you
the
wondering, do you
impact.
see these same effects on the asteroid?
That's right. What I don't know is how directly can I relate the behavior that I'm seeing, like the amount of spectral change or where these samples fall with respect to samples that I make on the surfaces. How directly is my
I think that's
laser
we
to?
can chat about that.
I was going to say,
Oh,
if you have
I'm
a really
just
quick
curious.
response, great.
Yeah.
Otherwise,
Sure.
maybe could you follow up during the intermission?
Yeah, that's
Yeah.
fine.
You guys know where to find her.
I think that and also it's what we have. So for right now, this is kind of our go for what it would look like, but it might not be the most accurate, but it's as close as it can be.
Let's thank our students.